Hey everyone, and welcome to another edition of The Explainer. I am so incredibly excited to have you here today. We love taking these big, complex concepts and just breaking them right down so we can really understand the world around us. And today? Well, today we're looking at an everyday, completely overlooked miracle. In fact, you're literally looking at it right now. We are going to unpack the incredible, entirely invisible magic of how television actually works. So, here's our roadmap for the day. We're going to cover the magic of television, the mechanical spinning disc, the electronic television race, how electronic television works, and finally, the evolution of screens. But hey, don't just look at this as some boring table of contents. Think of this as a massive technological mystery. We're about to go on a journey filled with farm boys, intense corporate espionage, and a brilliant biological trick played directly on your own eyes. Okay, let's dive right into Section 1, the magic of television, an everyday miracle. It's crazy, right? This technology is so utterly normal that almost nobody stops to think about how strange and honestly magnificent it actually is. Right this very second, in living rooms all over the entire world, screens are glowing with moving pictures beamed in from somewhere else entirely. Just think about that for a second. We are taking a camera in one location, capturing the light bouncing around a room, turning that light into something completely invisible, firing it through the air or down a cable, and then reassembling it somewhere else as a perfectly clear picture that you can watch in real time. That is the fundamental magic of television. And to really grasp how this modern marvel works, we actually have to take a step back in time. Which brings us to Section 2, the mechanical spinning disc, our very first attempt. Let's trace this timeline, because the historical progression here is just fascinating. The foundational idea for all of this started way back in the 1880s. Yeah, the 1880s. A German inventor named Paul Nipkow patented a mechanical system built around a spinning disc. Now, his idea was decades ahead of the technology needed to actually make it work, but he planted the seed. Fast forward to 1925, and a Scottish engineer named John Logie Baird used a very similar disc to put on a public demonstration of a working mechanical system. He refined it so well that by 1927, he gave the first true television demo in London. And then, by 1928, look at this incredible milestone. His company achieved the very first transatlantic television transmission between London and New York. No way, right? So, you might be wondering, how did this early version actually pull this off? Well, Baird and Nipkow systems operated on a core concept called scanning. Basically, they broke an image down into a sequence of tiny pieces. They did this using a really heavy spinning disc punched with a spiral of small holes. As the disc spun rapidly, light passed through those holes and hit a photoelectric cell. That cell cleverly converted the light into an electrical current. That current was then sent away and used to rebuild the exact same image on the receiving end. And, it genuinely worked. But it had a really hard ceiling. Heavy spinning discs can only spin so fast, and they severely limit your resolution. If television was ever going to be sharp, detailed, and flicker-free, the clunky moving parts had to go. And that brings us to Section 3, the electronic television race, a true David versus Goliath story. The industry was at a massive crossroads here. On one hand, you had mechanical scanning, heavy, totally relying on those clunky moving parts, and stuck with low, blurry resolution. On the other hand, there was the dream of electronic scanning, absolutely no moving parts, relying purely on cathode ray tubes to produce a sharp, pristine image. The world desperately needed to make the leap from left to right. Now, what's really interesting about this is the intense rivalry between the two men racing to invent that electronic future. It's a classic David versus Goliath setup. On one side, we have Vladimir Zworykin, brilliant Russian-born engineer, solid background in television research, and fully backed by the absolute corporate giant of the era, RCA. His core invention was a camera tube called the iconoscope. On the other side, Philo Farnsworth. Farnsworth was literally a Utah farm boy, no formal higher education, working completely independently. Yet he somehow managed to invent a working, fully electronic system he called the image dissector. In 1927, at just 21 years old, Farnsworth had a working prototype. What followed was a bitter, deeply drawn-out legal fight. RCA claimed Zworykin's earlier patents gave them priority. But this is where the story gets almost unbelievable. The entire case hinged on an old high school teacher of Farnsworth's. Believe it or not, this teacher had actually saved a sketch Farnsworth made while he was still a teenager, just zoning out in a high school chemistry class.
That single drawing proved Farnsworth's idea predated Zworykin's, and the Patent Office ruled in Farnsworth's favor in 1934. Now, of course, Goliath still had the weight. RCA's massive manufacturing power meant they eventually dominated the market anyway, though they absolutely had to pay Farnsworth royalties. Mechanical television just couldn't compete with the sharp image of this new technology, and the all-electronic standard was officially born.
All right, let's move to Section 4, How Electronic Television Works, the Technical Breakdown.
We know the farm boy won the patent war, but how did his all-electronic invention actually function? The best way to understand it is to split the whole process into two parts: capturing the picture and displaying it. On the capturing side, the big secret is that a television camera does not record a full image all at once. Step 1, it scans the scene in front of it, line by line, moving unbelievably fast. Step 2, as it scans, it converts the exact brightness and color of each tiny point into an electrical signal. Step 3, it transmits that stream of electrical pulses over wires or through the airwaves. You've successfully done the impossible. You've literally turned light into electricity.
Okay, now let's look at the receiving end to see how this all comes back together. Older television sets used what's called a cathode ray tube. Step 1. Inside that tube, an electron gun fires a tightly focused beam of electrons at the back of the screen. Step 2. Guided by the incoming electrical signal we just captured, that beam sweeps across the screen, left to right, line by line, top to bottom, redrawing the entire image dozens of times every single second. Step 3. As the beam strikes a special phosphor coating on the back of the screen, the coating glows with the exact right brightness.
But wait, if it's just a dot rapidly drawing lines on a screen, why on earth do we see a solid moving picture? Well, that brings us to the real secret ingredient: human biology. Persistence of vision is a quirk of human vision where your brain holds onto an image for a tiny fraction of a second after it disappears. Because the TV redraws the screen so unbelievably fast, your eye doesn't perceive the individual scanning lines flashing in sequence. Your brain perfectly blends those rapid flashes together. We are literally tricking our own eyes into seeing smooth motion instead of a chaotic sequence of still images.
And finally, Section 5, the evolution of screens, from cathode rays to modern living rooms.
Once that electronic system was locked in, the technology just exploded, spread like wildfire. In 1939, it was mostly just a novelty attraction at the World's Fair, drawing these curious crowds. But by the 1940s and 50s, those heavy wooden boxes had spread rapidly into American living rooms. This single invention spurred the creation of massive broadcasting networks, modern advertising, and an entirely new television-based culture. The technology kept marching forward, bringing us vibrant color broadcasting, eventually ditching those heavy tubes entirely for flat-panel LCD and LED screens, and swapping analog signals for crisp digital ones. The screens got thinner, the pictures got sharper. In fact, the very screen you're watching this explainer on right now is the direct digital descendant of this exact historical timeline.
So what does this all mean? The absolute crucial takeaway is that through all of those decades of evolution, the fundamental job the technology performs hasn't changed one bit: turning light into a signal and a signal back into light. Capture the image as a signal, transmit it, and rebuild it fast enough and smoothly enough that it looks alive. That is the core foundation sitting underneath every single modern screen.
It's just incredible to think about the journey of this technology, isn't it? From heavy spinning discs punched with holes to a Utah teenager dreaming up a revolution while sitting in a high school chemistry class. It leaves us with one final thought. Next time you turn on a screen, will you see the invisible magic of a Utah farm boy's high school sketch? Thanks so much for joining me on this explainer. Keep your curiosity sharp, and I will see you next time.